Every watt of electrical power that a high-power LED does not convert into light becomes heat, and that heat must leave through the material beneath the die. The faster it moves away, the cooler the junction remains, the steadier the light output stays, and the longer the LED can operate without thermal degradation. A ceramic heatsink that conducts heat rapidly while expanding at nearly the same low rate as the LED die and its attachment layer. That is what silicon carbide brings directly beneath the package. Silicon carbide carries heat at roughly 120 watts per meter Kelvin, well above common oxide ceramics and high enough to pull junction heat into the surrounding air or liquid before the die reaches its temperature limit. Its thermal expansion sits near 4 parts per million per degree. Close enough to silicon and silicon carbide dies that the two layers grow and shrink almost in step. Copper, by contrast, expands at around 17, more than 4 times as much. And that mismatch is the root of the stress that breaks solder joints during thermal cycling. At an elastic modulus near 410 gigapascals, the heat sink stays flat under thermal load, which keeps the die attach layer uniform and the thermal path consistent across the full footprint. Every time a power device switches on and off, the stack heats and cools, and any difference in expansion between layers pulls the solder joint in shear. The larger that CTE mismatch, the higher the strain per cycle, and after enough cycles the joint cracks, the thermal path opens, and the device overheats. When the heat sink expands at nearly the same rate as the die, the shear strain per cycle drops toward 0, and the solder joint can survive thousands of on-off cycles instead of hundreds. That is the engineering reason a ceramic with a CTE near 4 is chosen over a metal with a CTE near 17. The joint lasts because the layers move together. Footprints commonly step from about 10 by 10 millimeters up through 20 by 20, 20 by 25, and 25 by 25 to roughly 50 by 50 for larger modules, with base thicknesses from about 2 millimeters to 10 depending on the thermal path the package needs. From there the form is matched to the assembly. A flat plate serves where a thermal interface material handles the air side. Fins are ground in where the heat sink faces airflow directly. Fin count, fin height, channel width, and any surface metallization for soldering or brazing are each set by the power level and the thermal stack the sink sits in. Mounted directly beneath a high-power LED die or a chip-on-board array, the silicon carbide heatsink pulls junction heat straight down through a short, high-conductivity path and spreads it into the fin structure below. The low expansion keeps the solder bond between the die and the ceramic intact across thousands of on-off cycles, the failure point that limits LED life when the heatsink expands faster than the chip. And because the ceramic is electrically insulating, it separates the thermal path from the electrical path without an extra isolation layer, which shortens the stack and cuts the total thermal resistance. At full power, the junction stays well below its rated limit, and the light output holds steady hour after hour instead of drooping as the die overheats. The same fin structure that pulls heat away during continuous use handles the surge when the light switches on from cold, because the ceramic's low expansion and high stiffness keep the die attached flat and bonded through the thermal shock. Precisely, the heat sink matches the die it cools. In expansion, in conductivity, and in the thousands of thermal cycles that separate a long-lived LED from a short one.